So this screencast is going to really come full circle as far as connecting thermodynamic data to our study of equilibrium. So in Unit 4, you spent time in equilibrium and studying those systems. And now we're going to connect Gibbs free energy, which we know if we want a reaction to be spontaneous, Gibbs free energy has to be negative. So we're going to look at that. We'll look at it mathematically, but it's also really important to understand conceptually what's going on. So we will hit kind of the conceptual side as we walk through. Now, this first section deals with non-standard conditions. And so everything we've been doing, we've been assuming that we are at standard conditions, which is 298 Kelvin. Remember, that's thermodynamic standard temperature, not gas law standard, and 1 atmosphere. So we know that enthalpy is not pressure dependent, so we didn't have to worry, when we were doing delta H if the pressures were different, but we have seen that entropy is temperature dependent. Something that's at a low pressure has more freedom to move. And so if it has more freedom to move around, then this side's going to have higher entropy than at a high pressure. And so this is derived for you in your book. It's not important that you understand how it's derived, but it is there. And so let's look at kind of what all this stuff means. So when we see this knot, we know that that means standard. And standard comes from the tables. And so if you want to find delta G, you can look in tables. So look in index and just do products minus reactants, making sure you use the coefficients from the chemical equation. So this is if you had standard conditions. This is non-standard conditions, which happens. I mean, you run reactions and you're not at standard conditions. So if we want to solve for delta G, well, it's a function of what it is at standard conditions. And then this is kind of your correction factor. And so this shouldn't, none of these terms should seem new. R is your universal gas constant, and you want to use the one that has joules in it. So the 8.314 joules per mole K, because of course these are in energy. Temperature is your Kelvin temperature, and then ln Q is the natural log of Q, which is your reaction quotient. And remember, you find Q the same way you find K, it's just products of reactants. But the reason it's called a Q and not a K is because you're not at equilibrium. Something special happens when you are at equilibrium. Alright, so that is the relationship between non-standard conditions to standard by correcting it with this little factor. Okay, so we're just going to go through one example. These are pretty straightforward. So they want you to calculate delta G, so non-standard, at 700 Kelvin. So that's your temperature. Here's your reaction. And they give you these initial pressures. And so, of course, these are initial pressures, and so from that you can find a Q. So rather than doing it all in one big equation, let's find our Q, and then we'll kind of work backwards. So Q is the pressure of CO times the pressure of H2 all over the pressure of H2O. All the coefficients are 1, and of course this doesn't appear in the equilibrium expression because it's a solid, right? So when I plug in for my Q, I'm going to just put these values in. So 1 times 10 to the negative 4th times 2 times 10 to the negative 4th over 0.85. So we get a Q that's pretty small, 2.4 times 10 to the negative 8th. Alright, so that's one of the values I need. The other value I need is delta G naught, or the standard Gibbs free energy. And so that we said comes from tables. So we go and we look up values for these guys. These two are going to be 0 because they're in their standard state, but these guys will not. So looking in the table, for CO it's negative 137, and for H2O gas it's negative 229. So I'm just going to do products minus reactants, and so Gibbs for this is positive 92 kilojoules. So I've got that value, I've got that value. So to solve for delta G non-standard, it's delta G naught plus RT ln Q. So delta G is 92 kilojoules plus, okay, this R is in joules, not kilojoules. So I need to do 0.008314 or my other option is to change this to joules and make that 92,000, but one or the other has to change. Times my temperature, and then the natural log of 2.4 times 10 to the negative 8th. Alright, so we get a delta G of negative 10 kilojoules. Alright, so you'll notice that at standard conditions, delta G naught was 92. That's a positive delta G. That means non-spontaneous. But under these conditions, right, delta G comes out to be negative 10. So at this temperature with these conditions, this reaction will be spontaneous as written, which makes sense because if you check out these values, these are really small, right? Which means this reaction needs to shift to the right in order to reach equilibrium. And so that equilibrium is your driving force, and so that's why this is spontaneous at these conditions. So we're going to take a look at this equation and look to see what happens when you're at equilibrium. So we said that during a change of state, delta G goes to 0, and at equilibrium now we see that delta G goes to 0. Notice that is not delta G naught. Delta G naught values are at standard conditions, right? But they're saying delta G, so the non-standard goes to 0. So if this goes to 0, you're at equilibrium, and then your Q becomes a K, because if you're at equilibrium, right, you find it the same way, it's products over reactants, this becomes a K. And so this is usually how you'll see it written, and all they've done here to get from this equation to that equation, right, is to bring this over to the other side, and then put the negative with this side, okay? This is an important little note. They talk about the smaller the delta G, the closer to standard state is to equilibrium, and the larger the delta G, the farther it is, right? We talked about this earlier. If you have like 125 kilojoules as your delta G versus a delta G naught of 10 kilojoules, right? Both of these would be considered non-spontaneous, but this one is even less spontaneous than this one, right? Because this is so far away from 0. This is closer to 0. So this is closer to becoming a negative number. So you can look at the magnitude and see. This is just talking about kind of the math behind, well, how do you get these numbers? I'm going to fill these in. I don't want you to really stress about it. It has to do with the natural log function. If you have studied the natural log function, there's one. This graph has an asymptote along the y-axis, and then it increases as you go this way. So really this section is just talking about, well, when is it positive, when is it negative? So for these, it says when will the natural log be positive? Well, anytime it is greater than 1. And then for this one, anytime it's less than 1, but greater than 0. Again, I don't want you to stress about the math of it. We're going to kind of go through conceptually how you do it. Just for time, we're going to cut to practice 14, and I'm going to run through 15 and 16 for you. And then if we need help on 14, we can certainly do that later. Alright, so practice 15. I want you to calculate delta G for the following reaction and determine if it's spontaneous at 25 degrees Celsius. Okay, well that's delta G naught, and that's just going to come from a table, right? Then they want you to figure out what the equilibrium constant is. So then they want you to solve for the K. So I said we could use a table, but then check out what they give us. They give us a delta H and they give us a delta S. And so rather than going to the table to figure out what delta G is, we can use this handy dandy relationship. Delta G equals delta H minus T delta S. Because we do have a temperature, it's 298. So delta G equals negative 91.34 kilojoules minus 298. Remember, this is in joules, so we're going to change it to kilojoules. And so we get a delta G equal to negative 104 kilojoules. So that's the value, and I forgot my little knots there. That's the value of delta G. It's a negative number, so this is spontaneous at 298. So then they want you to figure out the equilibrium constant. Well, delta G naught equals negative RT ln K, right? So we know our delta G, I can always get my R, just make sure it's in kilojoules. This is 298, and then ln K. And so we're just going to solve for that natural log. The inverse function is what we're going to have to use. So the inverse function is the base E. So if you look at your calculator, you'll see it. So we're going to bring all this stuff to the other side, and we end up with 41.9 equals ln K. So we're going to do this to both sides. Those two cancel each other because they're inverses. And we get e to the 41.9 equals k. So k comes out to 1.51 times 10 to the 18th. Now I want you to think about that k. K is much, much greater than 1. And back when we did equilibrium, what did we say when that was true? We said that products were favored, right? So that means the forward reaction is favored. Well, now we're connecting it to the thermodynamics. So we said that this delta G being negative means that it's spontaneous, right? So these guys certainly go together, and so that's kind of what the previous little blurb was trying to get at, looking at, when will it be negative? What does that mean for your K? Well, this is a really big K, and we already knew that products were favored based on what we learned about in equilibrium. Now you're seeing the kind of thermodynamic reason why. All right, so practice 16, similar. Here they've got delta H, delta S given to you. They want you to calculate the value of K at 298. And then assuming that these guys don't change, so assuming that we can still use those, they want us to calculate K at 100 degrees Celsius, okay? So we're going to work it out for 298 Kelvin, and then we're going to work it out for, what would that be, 373 Kelvin, okay? So we need a delta G naught, so we have negative 58.03 minus 298 times negative 0.1766. So delta G naught comes out to negative 5.40 kilojoules. So in order to find my K at that particular temperature, I plug in, I get negative 5.40 kilojoules equals negative 0.008314, 298 ln K, bring all this stuff to the other side, and we get 2.18 equals ln K. So K is equal to 8.84. So again, K is greater than 1, and K is, delta G naught is a negative number, so this means spontaneous, right? But it's kind of barely spontaneous because it's getting to that 0 mark. Okay, it's not as spontaneous as this guy was, right? Because this was negative 104. And so you'll notice that the K is not as big, right? Okay, so now we're going to recalculate it for 373, and so to get the delta G naught, delta H and the delta S are the same, but now we're going to plug in this temperature. Now, really, that's a negative 0.1766. Now really, these guys do change a little bit with temperature, but it's not an appreciable change, so it's not a huge deal. So for this, we get 7.84 kilojoules. So now we've got a non-spontaneous, right? So at a higher temperature, this becomes a non-spontaneous reaction. So now when we go to solve for our K, what would we expect to be true? Is it going to be a K that's as big as this? Because that's saying that products are favored. But this is saying non-spontaneous, so hopefully it makes sense that we would expect the K to be a smaller number. So negative 0.008314 times 373 times ln K. All this is going to be brought to the other side. We end up with negative 2.53 equals ln K. Do base E to both sides, and we get K equals 0.0798. Alright, so look, our K is less than 1, right? Reactants are favored, and this is our thermodynamic connection. It's a non-spontaneous reaction, so those two go together.